Hello, I'm Rich Kim, and it is my pleasure to present to you our work on JellyFish, a fast scheme list with multi-version concurrency control. JellyFish is about a new scheme list variant that reduces the overhead of maintaining multi-version of the data in a key-value store. This work was done in collaboration with researchers at Line Corporation, Tsushin University, Seoul National University, and Syracuse University. Before we get into the details of our work, I briefly talk about key-value stores. Key-value stores are used everywhere and is considered the de facto storage engine for many applications. It stores data in a simple key-value pair, making it easy to store heterogeneous data and to scale out as demands increase. For example, in the social media posting shown here, a key-value store is used to maintain the various data such as the main text, the image, and the comments. However, we notice that key-value stores such as RocksDB exhibit peculiar characteristics. While it performs well under points access such as put and get, it does poorly for operations that return a range of data such as scan. This phenomenon is exacerbated if the workload contains more updates and more data are buffered in memory. So we investigated why. From our analysis and experiments, we find that the scheme list data structure is the main culprit for this performance degradation. This was an odd discovery because a scheme list is typically used as a fast memory layer in front of the slow disk in a design, known as the log-structured merge tree. In an LSM tree, each layer maintains data in a sorted order while buffering data before merging them with the next layer. This particularly excels in a small write with decent read performance as the data are sorted in each layer. But in terms of the ranged scan, the scheme list provides very poor scalability. So let's get into the details of a scheme list. A scheme list is like a basic linked list, except that it is augmented with additional layers that act as the express lane. This allows nodes to be skipped when searching for data, allowing for a long and time complexity. In a key-value store, a scheme list variant of what we call the append-only scheme list is typically used. In an append-only scheme list, all writes, including updates, are treated as inserts with a different timestamp. This allows for concurrent reads and writes through snapshot isolation. For example, let's say the Bob currently lives in Louisiana or will move to Wisconsin. Instead of directly updating the node for Bob, a new node with an incremented timestamp of 5 will be inserted. While Bob at Wisconsin is added, we can still read Bob at Louisiana, allowing for concurrency. However, the append-only nature means that if an update occurs on a particular subset of keys, there will be multiple copies for the same key that will make the list traverse slow. For example, if Bob is updated 3 times, we still have to traverse the bottom layer through the obsolete data to get to the top. This design decision of a scheme list, the one that append everything for concurrency, makes ranged query extremely slow. And as you can imagine, as the memory buffer size increases, this overhead increases as well. So, to address the limitation, we designed a variant implementation that maintains a parquet list of values. Unlike the traditional approach of appending everything horizontally, JellyFish keeps keys in a horizontal scheme list, while growing a vertical list of different versions of data for the same key. This design entails 3 advantages over the previous design. First and most obviously, separating keys and version means that when scanning the entire data structure, we only visit the number of nodes equal to the number of keys in memory. This makes scans fast in JellyFish. Another advantage is that We use a fewer number of atomic compare and swap operation or CAS when updating the value because there is a significantly fewer number of points involved. This also means that there is less chance of CAS failures when two concurrent writes compete. Lastly, the design of JellyFish also improved the performance of point accesses. In a horizontally growing append-only scheme list, even after finding the right key, the search continues, because it may not be the right timestamp version of data. What's worse, finding the right version of data means that the scheme list has to be traversed in the bottommost layer. In JellyFish, however, all the keys are unique, so finding the right version is straightforward after finding the right key. So far, we only focused on the scheme list used in LuxDB for illustration purposes. When surveying other key-value store, we observed that each of them lack and list one of the categories among lock-free lights, concurrency control, and fast scans. JellyFish, however, is the only design that achieves all of these features. We built JellyFish on top of RocksDB with about 1,000 lines of code modified. We call this JellyFish DB. Our project is available on the following GitHub repository, and we encourage you to check it out. We compare JellyFish DB against a wide variety of key value stores such as LevelDB, RocksDB, WildTiger, and LMDB, and use DBBench as a microbench and YCSB linkbench as the real-world workload. Due to the interest of time, however, we will only present a subset of the evaluation results. First, let's see the microbench result using DBBench, a tool that is part of LevelDB and RocksDB. These two graphs show the get and scan performance with the x-axis showing the number of threads and the y-axis throughput. Recall that JellyFish separates keys from version and has a much more compact scheme list for finding the right key. Because of this, JellyFish DB outperforms RocksDB by 51% and more than 5 times for get and scan, respectively. For scan, RocksDB in shows the best performance because it updates everything in place. But soon you will see that this comes as a heavy cost for put. Two graphs shows the put performance, one for random insertion and another for updates only. As shown in the graph, JellyFish DB outperforms RocksDB by 8% and 16% for insertion and updates respectively. The underlying reason for this result is because JellyFish DB reduced the time to search for the right place to insert and update and reduce the number of CAS operations. As for the in-place update version of RocksDB, as you can see, it performs poorly because it has limited concurrency. Now, let's look at YCSB results. We ran 1 million operations for each of the workloads from A to F. Here we show the result for the 3 updates, intensive workload A, B, and F. We observed that JellyFish DB outperforms RocksDB by up to 93%. And here is conclusion. In this talk, we share our finding on the overhead of keeping multiple versions in a scheme list. Our proposed design of JellyFish relieves this overhead by separating the per key updates from the main key indexing. There are a lot of more compelling reasons for JellyFish, so we highly encourage you to check out our paper for more detail. Thank you, and we'll be happy to take any questions.